Hello and welcome. In this video, we will learn about transformers. Transformers are quite complex yet beautiful piece of work that emerged from last 5 to 10 years of progressive enhancements that we see in the field of NLP. So this video is about understanding those enhancements with their proper quotations of research paper, etc., understanding the beautiful maths associated with them, as well as using our Python to actually see those things into action. So we'll start with tokenization, embedding, then we jump over to embedding techniques. For example, TF-IDF, then word2vec, their mathematical formula. Then we see globe emerged, and those things helped us to jump over to BERT and actual encodings that is used there in GPT. So we'll see word2vec, CBOW, skipgram, and how they are like mathematically related. Then what is there in DeepSeek, and how embeddings are like generated when we start fine tuning, etc. When then we start with sequence to sequence model to jump over to attention and then to transformer eventually. So we see like how translations were there initially by basic encoder to encoder block. We see like when first this encoder decoder block was used for translating sentences that we used to see earlier also in case of Google Translate, and what was their challenges in the things. Like when we go ahead, we'll see a lot of small concepts like softmax is there, cross entropy loss is there, so that we can train the things, back propagation, gradient descent. A lot of things will keep coming, and we'll see these things in detail. And then we go with attention, like when it was first introduced, then we understand like what was there in that paper, so that we can understand what is there in the case of attention is all you need, and we can understand the basic transformer model. So when we reach here, we have a solid grasp of things to actually understand this big block of transformer architecture. Then we start with one by one. For example, we start with input embedding, we start with positional embeddings, we start with, then we see multi-head attention, add and normalization, feed forward, all of these things. So we start with input embedding, we code input embedding, then we see how outputs are coming, what changes are there. We jump over to positional, and we understand the formula, their transformation with the help of log, etc. So all of these things are covered in a very much detail. We understand the code written in PyTorch line by line. We see like how output is coming, what changes there. When these two are done, then we move forward to add a normalization. We understand that. Then we jump over to feed forward, covariate shift. So all of these things, as and when they come, our goal is to understand those things in a detail by taking relevant section of the paper and understand, so that a research mindset we can enhance that is there. So let's get started on the journey of learning transformers, starting with tokenization. And to learn transformers, the first thing that we have to do is understanding tokenization and embedding. So the thing that we are doing here is understanding what is your natural language processing, and for that we have tokenization or embedding, these sort of things. Now these all things are related to NLP, that is natural language processing. Now what is natural language processing? So as the name suggests, NLP is natural language processing, and in this we're trying to understand natural language. So what is natural language? Natural language is the one that we as a human can understand. Now the problem with natural language is that it is not something that a machine, or you can say computer, can understand. And as we know, computer can only understand mathematical or binary things. So we have to convert our language into what? Into numbers, so that computer can understand it. That's why we have NLP, that is natural language processing, and that's why we have tokenization and other things like embedding. So let's start with tokenization. So tokenization is about breaking given text into a smaller piece, and those pieces are something that we call tokens. So these pieces can be your words, subwords, or characters. For example, let's say this is our sentence, I love transformers. So the I love transformers have I love transformers and this exclamatory mark as well. So these are the individual words. So if we are splitting this particular text or sentence, we will get I love transformers and this mark, exclamatory mark. Hence we have these 4 tokens. So as you can see here, this is what word tokenizer, this first thing. So what is tokenization? Tokenization is breaking a text into a smaller piece, tokens, and then from these tokens we generate embeddings. Because let's say we have a large corpus of text. For example, let's say we have Wikipedia. Now Wikipedia have various sentence and we can't directly make embedding. That's why we go with the tokens, and for each token we generate embedding. Okay, this is not the root, this is the one. Okay, so tokenization is simple, but to understand embedding, there are other tokenization also. So let me do that also, like subword tokenizer or character tokenization. So subword is, for example, like transformer is not, let's say, is not in our vocabulary. So whenever you are making something called NLP sort of things, then you have to define a vocabulary. Vocabulary is like you will be having a limited like you have to process limited number of words. So those things are your part of your vocab. Okay, so in your vocab you might be having, let's say, 50,000 or 50k words. So if any word is about like outside of these vocab, so those words are marked with unknown or UNK type of symbol, okay, to generate token. So that's why this vocab is important. And if some new word is coming, and if your vocabulary is not knowing that what that word meaning is, then there will be so many unknown. That's why we have subword tokenizer. So subword tokenizer, like let's say if some new word is there, it will break that in smaller parts that may be known. For example, transformer can be broken down into trans and former, and S is different than exclamatory mark. So this is subword tokenizer. Okay, and it is used like in byte pair encoding, etc. internally. Then we have character tokenization, where like we are breaking each word into its individual character, and it's not that like obviously efficient, useful, etc. So primarily we are using subword tokenizer for like byte pair encoding, etc. So we'll see these things. Now let's come over to embedding, and then we will be able to understand this part a bit more carefully, or a bit more like intuitionally. Embedding is like how to make your neural networks or any other model to understand words. If you have worked with machine learning or these sort of things, then you might be knowing that, let's say you have a model, like let's say we are building a neural network. You will be providing some x, or you can say let's say this is a matrix vector x1, x2, and x3. So you will be providing some numbers or some data, and each will be having a weight w1, w2, w3, or you can say w11, w12, w13, like this. Then you will be having w21, w22, w23. These all are numbers, and you will get some output y. Okay, now but in the case of natural language, we are having what sentence, just like I have written here. This whole is a sentence. How you make your this model understand this sentence, and that's why we have what generating the embedding of it. So, and this whole attention mechanism is only about how you can generate superb sort of embedding. Why we need embedding is about, because machine learning models can't directly process text, because they can only understand numerical data. So we need a way to convert your text into numerical form while preserving its meaning and relation between words. This is the most essential and the crux of this whole transformer thing, that we need to convert text into numerical form. but in such a way that we have its order, its meaning, its relation with other words as it is. That should not be like lost. That's the like important part, and we will see this in like much depth when we will talk about attention mechanism or sequence to sequence modeling. So this part will keep on coming again and again. So first thing is tokenization. Tokenization converts words into tokens, and from that we generate embeddings. So embeddings is convert input tokens into dense vectors. Input tokens into dense vector is embedding. So converting word to numbers. Model can capture semantic relationship, and similar words have similar vector representation. This should be there as well. We'll talk about semantic and syntactic relationship as well, but you can say semantic means, let's say I have bad, I have worse, I have for example these two were same, good, amazing. So these carry kind of same thing, right? Or if I say happy, if I say delighted, so these things, these words are similar. So they are carrying some sort of similar semantic relationship that we have to. Now our numbers or the vectors that we will generate from these words, they should be same. They should carry some similar kind of meaning in them, in the numbers itself. That's the aim of this whole embedding thing. All right, so let's see these things into action. We have seen that tokenization is the process of converting text into meaningful units that are tokens. We need tokenization because we will be having a lot of text and we want to convert them into some tokens. So let's get these things into action. So I'm connected in Google Colab, and the first thing is we need import NLTK library. So import NLTK, and we have to download the punct2 that is suggested here. So let's see these things. All right, and then let me add few tabs here. So okay, let's see about NLTK library also. So as you can see, NLTK is natural language toolkit library, and it have a lot of things. So we can just use like word tokenize or sentence tokenize, these sort of things, to get proper understanding of this. So I'm just copying text from here. Okay, so let's make some text in some string, and there you go. Okay, now we have added text. Now we'll import from NLTK dot tokenize. We can import word tokenize, sentence tokenize, and then we can pass our text to get the tokens. So we will pass the text that we have defined above into word tokenize and pass the text, and let's get print tokens. Rather it is like, because they are multiple, so okay, so we are seeing this error because we have not downloaded this. So let's copy NLTK download here only to download NLTK punct tab as well. And here you go, you can see we have tokenization of that above sentence. For example, NLTK is a leading platform, so you will see NLTK is a leading platform for all of these things are coming, and you can see dot also coming as a separate token that is there. Okay, and you see is easy to use, it have made a separate token rather than having separate. That depends on like what in like how internally it is working. You can see comma is there, with is there, numbers are also like converted as well into tokens. So these things are good to see, these things like this word tokenizer into action. Let's see the second thing is sentence tokenization. So if we use sentence, so we will get multiple sentence tokenized. So we can just use like this tokens. So tokens equal to send tokenize, and we'll pass the text and then print out the tokens. There you go. Now you can see this whole sentence is coming as first item, and then second sentence is coming as the second item. So this is your sentence tokenize. Other one is like character tokenize. We can just we can just pass into list and it will make that part as well. So character tokens equal to list of the text. and then we can print char tokens. So all of these characters are coming now as the individual tokens. So this is the idea of word tokenize. We have seen splitting text into words, splitting text into sentence is sentence tokenization, and then character and subword. Now let's see about subword. That's the main important thing that we have to see. So we have used like byte pair encoding, word piece, and sentence piece. These are the important thing. And byte pair is used, BPE is used in GPT or OpenAI models. Word piece is used in BERT, Albert, etc., and sentence piece in the case of Google T5. So these are like uses of these uh, sentence. So these are uses of these various tokenization algorithm in various LLM architecture. We will see these things like how BERT differ from T5 and how GPT differ from other variant. So they have like some difference, whether they are encoder only, decoder only, whether they are using both. These type of internal differences are there. When we'll jump over to those part, we will see those things as well. But for now, let's focus on subword tokenization with the help of byte pair encoding. So for now, let's focus on subword tokenization with the help of byte pair encoding. Let's do pip install tokenizer also. So both will be installed, transformer and tokenizers. After that, let's import few things from this tokenizer. So from tokenizer, on the basis of that, we will like make the instance, the main object we will have to make. We have to install models, we have to install trainers, and we have to install pre-tokenizer as well. After that, we have to create a tokenizer. So let's create a tokenizer, and then we have to pass the models dot. We are passing since we have to do in byte pair encoding, so we will use byte pair encoding as the model. So it is creating byte pair encoding tokenizer, and this tokenizer does not have any predefined vocabulary yet. We need to train it first, then we have to use it. So you can see this have to be trained first, and then only we will be able to use it. That's important. So it's about now how to train it. So before that, we have to like handle the space also, so that we can like add white space or meta space before using it. So let's do that also from with the help of pre-tokenizer that we have imported already. So tokenizer dot pre-tokenizer is equal to pre-tokenizer dot, and we will be using meta space here. So meta space preserve the space with replacing them with the underscore. For example, let's say we have this line. So let's say we have this line, it will be replaced by underscore leading underscore platform, like this. So it keeps the space there. After that, we have to like define our text on which we want to train. So yeah, other options also you can have a look, like there's white space, there is byte level. Byte level is used in GPT-2, and white space is splitting text on basis of space. So, and this is a meta space. Let's define corpus. So corpus are the sentences that uh, with the help of which we will train our model. The bigger the corpus, the better the performance of our tokenizer, and we can use millions of lines of text from some books, Wikipedia, etc. And the last step is training the tokenizer. So we will use trainer equal to trainers dot BPE trainer with the vocab size, and we can pass some special symbols, and we have to pass the corpus later on in the trainer. So for that, we will use this trainer in our tokenizer. So tokenizer dot train from iterator with the corpus and trainer. The trainer is our about trainer. So now we are like training it, and we have the corpus defined here, and we have the trainer. So as you can see, this was totally new. We have provided some text, then training it, and later on, and at this state, our tokenizer will be trained, and it have some meaning. So then we can like use it. So how to use it? By the help of encode. So tokenizer dot encode, and we can encode any text. Like tokenization helps in text processing, and then we can print the tokens. And how you print the tokens? So first store this. Let's say these are coming in encoding, and we will print encoding dot tokens. There you go. Let's run it, and you can see our tokens are coming like this. Tokenization helps in, and there this much are coming. And the problem, like, these are not merged are because our corpus is small. Let's add few more lines to make our model more like trained. As you can see, let's have these two lines also. I don't want to add some links, so that's why. Cool. This is one line, comma, and this is your second line. Now let's see like what improvement it makes. All right, now we have little improvement. As you can see, it is not able to understand processing because in our sentence processing is not there. So let's add processing somewhere. Let's say I added here. Let's say I added here. So you see processing came. So how BP is working, that's important. So byte pair encoding is a simple method where we like break our sentence in some characters, in each characters like T, O, K. Then it takes like what are a common occurrence, like TO is coming how many times. So TO is coming, as you can see, 1 2 3 4 5 6 times T and O are coming. Then it will check OK, how many times OK is coming. So you can see 3 4 times OK is coming. Then it will see these type of clubs. Then it will make how many times TOK is coming. Then it will make how many times whole this word is coming. So on the basis of frequency of occurrence of this clubbed words, it define, okay, this should be a sentence, this should be a word because it is coming a lot of times. And it will make a kind of a occurrence frequency here in the case of byte pair encoding. So this is how BPE works internally. So it makes like how many times each uh, character tokens are occurring, the and it merge frequent pairs, and it repeat until vocab size is like our optimal, like okay, we only need 50k vocab, so that up to a certain size it runs, and that's how it is processed. Okay, let's take an example to understand it better. Let's assume like let's say in our corpus these were the words only: low, lower, newest and widest. Okay, now so it will check, it will split into character level tokens. So each word will become character. For example, here low will become this, lower, newest and widest, like this. Then it will merge the most frequent pair. For example, and O, L and O will be become LO, like this. So at next step it will become something like this. It have merged these things, and after that it will repeat for O and W also. So something like this. And eventually, let's say we need a certain word, like okay, or we need only 5 words, 10 words. So we will keep merging, and we will become, our vocab will become something like this. If we go ahead, it will become lower, then newest, wide. So it depends. Okay, if we need 1 2 3 4 6 words only, we can stop it here. So something, this is the internal working of byte pair encoding. If you go to OpenAI tokenizer, play around. So if I, let's just copy this, uh, and you will see tokenizer in action. So you this it have 48 tokens with 267 characters, and you see this is one token, this is another token, like this. In the case of GPT-3, like all the models are there. So this is one way where we have seen. Uh, so this is one way where we have seen importing a tokenizer, training it with some text, and then using that tokenizer that we have trained to encode a text, and then we can get the strings of like numbers of it. So that is there. Now what if we don't want to use it directly, and we don't want to, what if we don't want to train it, but want to use pre-trained already, so that also we can do. So for that we have to import from transformers library. So from transformers import auto tokenizer, and we will use tokenizer equals auto tokenizer dot from pre-trained. We can use rather than BART, let's use GPT. So let's say we are using GPT-2, and then we will encode the token. So tokenizer uh, encoding is tokenizer dot tokenize and the sentence, and then we'll get the tokens. Tokenizer dot tokenize, and we will get the tokens encoding. It imports, and then you can see we got the output. Helps in text processing, something like that. We got the individual token that are there as per GPT-2. So we got this output. That's it. So this was about byte pair encoding. So you understood byte pair encoding, how it is working. The main crux of byte pair encoding is about uh, server tokenization. It is, and it is widely used in uh, handling tasks, because you see the benefit of, if we have to write byte pair encoding benefits, so we will say that it is good because it is handling out of vocabulary problem. It breaks down unknown words into subwords, and those subwords are known. So it is solving out of vocabulary problem. It reduces the vocabulary size. Instead of storing all the words, it only stores subword patterns that are there. For example, as you have seen here, token and ization is used, and this can be clubbed with many other words, and it improves the performance also in it improves the performance also in some language like Hindi, or let's say Japanese, where word variation is very common. So the benefit is about solving the out of vocabulary problem, reducing the size of vocabulary, and in some rich language like Hindi, etc., it is very useful. So byte pair encoding is start with the character level token and then merge the most frequent token pair to get our like number of tokens that we require. So in this particular session, we have seen about word tokenization, sentence, character, subword by with the help of byte pair encoding. There are others also, for example, SentencePiece, or if you see here, one second, yeah, if you see WordPiece is there. So WordPiece is similar to byte pair encoding. The difference is we are using WordPiece is similar to byte pair encoding. The difference is that in the case of byte pair encoding, we are using frequency of occurrence of like common pair, and in the case of WordPiece, we use in the case of WordPiece, we use probability distribution of the words. That's the difference. And SentencePiece is different. It is unsupervised model. So it is not space dependent, and it is used in T5, etc. But it is good. Like SentencePiece is good because it works on Asian language like Japanese, etc., Hindi, etc. So that's there. So as far as tokenization is concerned, this is all that you have to know. And because we are more focused on byte pair encoding, so we made our own model. We trained with some text, and we got output on the basis of how much having. Or if you don't want to train, you want to use already pre-trained model. So we did that also. Now this is from pre-trained model of GPT as GPT itself. So you can use that also. So we have seen both the ways, and that's all.